Today, we're diving into a fascinating engineering mystery. It's a story about how the exact same code can get slower and slower and slower over time, all because of some hidden forces lurking inside your JavaScript engine. Okay, let's get into it. So it all kicked off with a critical user profile API. When it first launched, it was screaming fast. I mean, a 6-millisecond response time. But fast forward 1 year, with no big code changes, and that same API was now taking 28 milliseconds. That is a 4 times slowdown. For a core part of a product, that's a total 5-alarm fire. So, what on earth was going on? Why was the very same code handling basically the same kinds of requests suddenly running 4 times slower? This wasn't just some simple bug, it was something way, way deeper. As you can imagine, the team immediately launched an investigation. This was a true mystery at scale, and they had to hunt down that bottleneck before it started seriously degrading the entire user experience. So they started with all the usual suspects. You know the drill. Was it the infrastructure? They threw more CPU and memory at it. No luck. What about the database queries? Already optimized. The cache? Perfectly tuned. They even profiled the code line by agonizing line, but nothing explained this huge, creeping slowdown. They were hitting a total dead end. And then, the breakthrough. Someone on the team had this brilliant idea. What if they checked to see if latency was related to how old a user's account was? And bingo, that was it. Brand new accounts were fast, old accounts were slow. The mystery suddenly had its first real solid clue. Okay, so what was so different about older accounts? You'd think maybe they just had more data, right? But it wasn't the amount of data. The real hidden culprit, the thing that was causing all the pain, was the data's structure. Just take a look here. On the left, you've got a new user object. It's clean, simple, consistent. But on the right, that's an older one. See, over the course of a year, as the team added new features, it just grew and grew, accumulating all these optional fields like verification badges and premium status. Each new feature created a slightly different object structure, and this whole phenomenon actually has a name. It's called object shape diversity. It sounds technical, but it's really just what happens when objects that your code thinks are all the same type actually have different properties, or maybe even the same properties but in a different order. And this tiny, seemingly insignificant detail is exactly what was wrecking the JavaScript engine's performance. So to really understand why this diversity is so deadly for performance, we need to pop the hood and look inside the engine itself. Specifically, Google's V8 engine, which powers both Node.js and Chrome. Let's see how V8 tries to be incredibly fast and, well, how our code completely broke its optimizations. Okay, so V8 uses this incredibly powerful trick called inline caching. Here's how it works. The very first time your code tries to access a property like user.name, V8 has to do a slow search to find where that value lives in memory. But it's smart. After it finds it, it memorizes the object's shape, basically its layout, and where the name property is. Then, the next time it sees an object with that exact same shape, it just skips the whole search and goes directly to the right spot. It's a massive, massive shortcut. Now, this shortcut kind of has 3 different gears, and which gear you're in all depends on how many different object shapes the engine sees at that spot in the code. If all the objects have just one single consistent shape, the cache is monomorphic, mono for one. This is the absolute fastest state. If there are just a few different shapes, say between 2 and 4, it's polymorphic, poly for many. That's still pretty fast, but, and this is the important part, if you have more than 4 shapes, well, the cache goes megamorphic. And at that point, V8 just gives up. It throws away the shortcut entirely and goes back to doing that slow, painful, full lookup for the property every single time. The performance penalty here is staggering. We're talking up to 100 times slower than the optimized path. This right here is exactly what was happening to that API. So you have to wonder, how did they get into this mess in the first place? Well, it all came down to a classic engineering trade-off. The need to move fast and be flexible versus the hidden chaos that flexibility can create down the line. The crucial insight is this one right here. The team, with the best of intentions, wanted to add features quickly, and just tagging on optional fields seemed like the easiest path. But as the source material points out, what they had accidentally built was a system where every cool new feature was slowly poisoning the performance of their most critical code. No, look, there are other ways to design something like this. They could have used version schemas, but that means you're dealing with really complex and sometimes risky data migrations. Or they could have separated the stable fields from the changing ones, but that makes the code itself way more complicated to write and reason about. There really are no easy answers here. So, armed with this new knowledge that the root cause was object-shaped diversity, the team set out to restore order. They had to tame the chaos they had accidentally created to get their speed back. And the fix was actually pretty elegant. They defined what's called a single canonical shape that all user objects had to follow. Now, instead of just omitting optional fields, those fields were always included but just set to null if the user didn't have them. They also made sure the properties were always added in the exact same order. This little bit of discipline forced every user object to have the exact same shape. And the result? Boom. Latency dropped right back down to that original 6 milliseconds. Performance was fully restored. By forcing all the object shapes to be the same, they allowed V8's inline caches to snap back into that super fast monomorphic state. A perfect full circle moment. But they didn't just stop there, which is the really smart part. To make sure this kind of thing never, ever happened again, they built custom metrics to actually monitor the state of their inline caches in production. They could now literally see if a piece of code was becoming polymorphic or, even worse, megamorphic, and then fix it before it turned into another crisis. You know, this whole saga teaches a much bigger lesson, one that goes way beyond the specific bug. It's really about adopting what we could call the architect's mindset, designing your code not just to be correct, but designing it for the runtime environment it's actually going to live in. Here's the core takeaway, the big lesson. You have to start treating an object's shape as part of your performance contract. It is not just some minor implementation detail. It's a fundamental promise you are making to the runtime engine. For high-performance code, it's not enough for it to be logically correct. You have to think about how the data structures you're creating will actually behave when the engine tries to optimize them. And this chart just drives the point home perfectly. Look at the cost of chasing the wrong problem. Months were spent trying to solve this by just throwing more expensive infrastructure at it, when the real fix, once they understood the problem, took just a few days. Understanding the runtime wasn't some micro-optimization. It was the most direct and cheapest path to a solution. And that brings us to this powerful conclusion from the source material. Inline caching is not an implementation detail. It's a fundamental mechanism that determines whether your code runs fast or slow. This isn't some obscure feature for engine nerds. It's at the very heart of JavaScript performance. And that's our story. It's a bit of a cautionary tale, right? And it leaves us with a really important question we should all be asking about our own work. What performance time bombs might be ticking away, hidden deep inside your code?